represent a normal distribution of the population to look something like this: a bell-shaped curve, symmetrical around the means. Mean is usually in the middle with the median. It's almost all of the values are within 3 standard deviations of the mean. 95% of the values are within 2 standard deviations of the mean. And this generally represents a typical normal distribution. In this particular case, the mean of this population is 100 and the standard deviation is 10. As you guys have heard before, when we use the Greek letter mu and the Greek letter sigma, we're referring to parameters or population means and standard deviations. When we use x bar and we use s, we're referring to the mean and the standard deviation of a sample rather than a population. Okay, so one of the things that we learned when we did that sampling exercise last week was that if we take this population and we were to go into this population and repeatedly take samples of size 4, if I took an infinite number of samples of size 4, I just kept randomly picking 4 people out of this population and finding the mean, and 4 more people and finding the mean, and I plotted that new distribution of those means, well, we're not going to, when I take 4 people, we're not going to get 4 randomly selected people who are all at the very end here, all at the other very end here. More of our samples are going to be clustered closer to the middle for these sample means. So our sample distribution is much narrower. In terms of standard deviation, if sigma is equal to 10, the standard deviation of the population is equal to 10, well, we can calculate the standard deviation of all of the samples from that population by taking the standard deviation, 10, and dividing it by the square root of the sample size. Square root of 4 would be 2, into 10 would be a standard deviation of 5 for all the sample means. We give that a new name. We call it standard error, but it's really standard deviation of the sample means. Now, if I go a little further, if the sample size increases, then each sample that we take is going to be a better representation of the mean. It's going to be closer to the mean. So the distribution of all those sample means is going to be even closer to the population mean. There's going to be less spread there. If we look at the standard deviation, it's 10, still 10. Sample size is 25. So the standard error or standard deviation of the sample means is going to be 10 divided by the square root of 25, or 5. 10 over 5 is equal to 2. So 95% of those sample means of size 25 we would expect to be between two standard deviations, which is 2, or within 4, between 96 and 104 if we were sampling from this population. 95% of the time, that's where we would expect our samples. And you can see that as we increase the sample size, the standard error gets smaller, and our distribution of sample means gets narrower and narrower. Okay, so we're going to actually put this to work so that it can do something for us. Okay, so now one of the things that we're interested in is, let's say we take a single sample and we find that single sample gives us a result that we call X bar, or mean for the sample. And we're interested in knowing, well, that's the mean for the sample. If I repeated this over and over again, how would I expect more samples to fall? Where would I expect this range of samples to be? And again, we'd expect 95% of the samples to be within 2 standard deviations above the mean and below the mean, or since we're dealing with samples, two standard errors. Well, you guys might have remembered that when I say 2, I was using the empirical formula. In other words, that roughly 95% is between -2 standard deviations and +2 standard deviations. In reality, the real number is the z-score, the number of standard deviations below the mean and above the mean, where 95% of the values are, is really 1.96. And just to show you that I'm not making that up, I'm going to go to the z-table. Here's our z-table. Z-table tells us that, I'm going to go up to here, that everything to the left of this line, of that z-score, right, is represented by an area in here, like a z-score of negative 3.4. It's way down here. So only a tiny amount, or 0.03% of the values are below a z-score of negative 3.4. And of course, a z-score 0 is the mean, and 50% of the distribution would be there. But in this case, we want to know, well, no, I want to know what z-score represents a value where 95% of the values are going to wind up between that z-score and its mirror image on the upper side. So in other words, we've been assuming it's 2, negative 2 and positive 2. Let's see what it really is. These numbers in here represent the areas of the distribution. As the z-score goes up, that area gets bigger. So let's find out, what does that area have to be for 95% to be in between? Any guesses on that? What's that area have to be for 95% to be between that value and a value at the top? That's the same area, right? I'm gonna need that to be 2.5%, right? 2.5% here, 2.5% there, leaves 95% in between. So I'm gonna look for 2.5%. And as I look here through here, here's 2.5% right here. And that represents a z-score of negative 1.96. So really, what I need is, well, actually, 1.96 is, we want the z-score. Oh, right, 2.5%. Thanks. Exactly right. Got a little bit of a delayed reaction there, so I got a little confused. But you're right, exactly, 2.5. Okay, so we need to use a z-score of plus or minus 1.96 when we calculate the percentage the z-score that represents 95% of the population. Okay, so now we've last week we talked about the confidence interval, and we determined that based on what we know about these distributions and the way that what the sample means are distributed when we repeatedly sample, we decided that, well, we would expect that 95% of the samples are within 95% of the time that we will capture the population mean if we take a sample, if we give it this range in addition to the mean. So, in other words, let's take this example. Okay, in this example, we know that the mean of the sample is equal to 98. We know that the population standard deviation is equal to 10. Well, that's kind of an artificial situation, right? We really don't know what the population standard deviation is in most cases. I'm going to say that we do. Perhaps it was determined by another study or a census or something like that. But in fact, that really never does come up, right? Because we don't really know the population standard deviation. But in order to calculate the standard error for all of the samples that we might have, we need to know that. If we don't know that, then we're really just estimating the way that this is distributed. We have ways to get around that, to improve our estimate and to deal with not knowing the population standard deviation later on. But right now, let's assume that we know it, and we can calculate our standard error. So if I wanted to calculate the 95% confidence interval, I would take my mean, add and subtract 1.96 times the standard deviation for the samples, or the standard error from that. Okay, now this number 1.96 times the standard error, this whole section right here, I'm adding and subtracting that from the mean in order to get a range. So let's figure out what that's going to be. It's 98 plus or minus 1.96 times 10, the sigma, which is the population standard deviation, divided by the square root of 100, which is the population, 100. That's n, is 10. 10 over 10 is 1. So 98 plus or minus 1.96 times 1 is 98 plus or minus 1.96, which comes out to 96.04 to 99.96. Basically, what we're saying is we are 95% confident that the true population mean, based on what we know about our sample, right, that the true population mean is between 96 and 100, basically. Okay, does that mean that we know positively what our sample mean is? Somebody give me an opinion. Do we really know what our sample means? What's the probability that we're wrong? That the population mean is not between these two? Can anybody tell me what the population is, what the probability is that we'd be wrong? And it would be either lower than, right, 5%. If we're 95% confident, that means that we're accepting a 5% chance of being wrong. Exactly right. Not sure what the question marks there, but you got it right. Okay, so that's really what we're dealing with here. Let me mention one other thing here. We are subtracting and adding this value here. We're saying that we think our mean is 98, give or take this value of 1.96, right? Because the standard error happened to be 1. If it were 2, it would be plus or minus 4. If it were 4, it would be plus or minus 8, and so on and so forth. What's a good name for this value that we add and subtract from the sample mean? Anybody got a good name for that? What would you call that plus or minus 1.96? I'll give it to you. I'll rephrase this another way. Let's say I got $20 in I think I have $20 in my wallet, but I tell you, I think I have $20, give or take $5, plus or minus $5. What would you call that plus or minus $5 in ordinary parlance? Right? What would that be? That'd be a margin of error, right? This number is your margin of error. Okay, it's going to come up in some formulas later on as the value m, but that plus or minus whatever this resolves to, the plus or minus 1.96 times the standard error is our margin of error. Okay, so let's move on to another one. Now let's say, I'm going to jump to this one. Let's say we want to be more confident that about the range within within which we're capturing the mean. We want to be 5% chance of being wrong is too much of a chance for us. We want to be 99% certain. Okay, what do I do? Should I make that a wider range or a narrower range to be more confident? What do you guys think? Wider or narrower? Okay. In other words, should I move? Should I say before it was 90, what was it again? Let's see. It was 96 to 99. Should I make that a wider range or a narrower range if I want to be more confident of catching? Right. You want it to be a wider range. A wider range is going to be more certain of capturing the population standard deviation. Right. So let's take a look at this. Let's say we want to be 99% certain. That means that we want to have this range have a z-score that leaves only 0.5% of the possible outcomes out here and 0.5% here to add up to 1% where we would miss it, and 99% of the time it would be between the real population mean would be between these two values. So now instead of my margin of error being 1.96 times my standard error, I need to use a z-score here that affords me a probability of 99% chance of catching the mean, only 0.5% chance of being low or high. So I'm going to go back to the z table. Here it is, still handy. And this time we want this area to be 0.050, 0.050, 0.5%. Okay, let's see where we are. 0.05. Here we go. This is pretty close. 0.0049, and that value is negative 2.58. So if I go back here, I'm going to use the value negative plus or minus negative 2.58 times the standard error. Okay, so if I look at this, let's see, 2.58, it's exactly the same problem.
Call from.
It's exactly the same problem. The standard deviation is 10. The sample size is still 100. The mean is still 98, except we're going to calculate a 99% confidence interval. Well, in this case, we still have standard error 10 over square root of 100, which is 1. It's going to be 98 plus or minus 2.58 times the standard error. 98 plus or minus 2.58 is 95.42 to 100.58. Okay, so automatically that does, no, it's not a narrower graph. It just spreads out it's the same graph because it's the same population, same sample size, same standard deviation. We're just using a higher number for z so that we get a wider range, that we make it more likely we're going to capture the population mean somewhere in here. Okay, and less likely that the population mean for this particular case would be outside of here. Okay, so similarly, if we're willing to accept more error, we can use a confidence interval that's smaller, 90% confidence interval. And in this case, 5% can be in this tail, 5% can be in this tail. And if I go up there to z-score that I'm going to need for this, and you can take my word for it rather than going back and doing it again or look at it yourself, we would use a z-score of 1.64. So just changing the z-score to one that represents the confidence level that we want, right, allows us to determine what the range, what the margin of error has to be in order to satisfy that confidence interval. And we can calculate that confidence interval for any percentage that we want based on the Z table. Now remember, all of this is based on the assumption that we know what the population standard deviation is. Well, things aren't that don't always work out that way. In fact, they almost never work out that way. There's a 99% confidence interval. Okay, so now let's take a look at this. Okay, now in this case, we're working with a 95% confidence interval, except this time I'm going to take a short a side journey here, just to mention to you that in many cases, we're working with means and standard deviations of scalar numbers. In other words, real like numbers like 100, 50, 35, and so on and so forth. Many studies use proportions in place of those numeric scales. Okay, for instance, you might be interested in what the probability that someone in a population has diabetes, and you might sample 100 people and find 15 people in that group have diabetes, and you say, okay, 15 out of 100, the proportion of diabetes in its population appears to be 15%. Well, gee, the problem is that if you took another sample of 100, you might get a slightly different value, and a slightly different value in another sample. And just like before, you would have a sample distribution, except this time, instead of a mean, you would have an average proportion that you would be looking at. Okay. So now let's say that we're surveying people to see how many of them have ever had a cold sore on a lip or something like that. Okay. That's I guess herpes simplex 1. Okay. Have you ever had a symptom that would match that? Okay. And we survey people. It's fairly common. So we're going to say, for argument's sake, 60% of the population has experienced that. Okay, so we do a survey of 100 people. 60% of the population of that 100 people say that they've experienced that. We're going to call that proportion, 60 out of 100 people, or 0.60, we're going to call that P cap. Okay, I added the cap there because frequently I'll type it out instead of using the P with a little caret on top, right? So you'll see me do it either way. So P cap is equal to 0.60. Now keep in mind that that's a sample proportion of a sample of size 100. But we have a formula that will allow us to calculate the standard deviation for repeated samples of size 100, the proportions that we would be likely to get based on chance if we truly randomly sample. That the standard deviation, or the variability for those samples, or standard error, is going to be equal to the square root of P times 1 minus P over the sample size. P represents the probability, true population proportion of that event, that reporting having that condition. So P times 1 minus P would be 0.40 divided by the sample size of 100. Now, we don't know the true population proportion, P. We only know P cap. So in order to use this formula, we have to satisfy a certain rule that the sample size that we're working with is big enough that we won't have in either P or 1 minus P a sample size of less than 15. So we want a sample of at least 30 people, meaning at least 15 in each group. So in this particular group, since P cap is 60%, that's 60 out of 100. 1 minus P, that's a little bit backwards. 1 minus P is 40, right? Because 60 had the condition, 40 didn't. So in both cases, they're over 15, and added together, they exceed 30. So we can go ahead and use this calculation for standard error. So standard error is going to be equal to zero point 0.6 times zero point 0.4, which is divided by, which is 0.24, divided by 100, which is 0.0024, and the square root of 0.0024 is 0.049, or about 0.05, about 5%. Right? So now let's go back here. Well, our p cap plus or minus our margin of error, the z-score we're going to use, times the standard error. We're going to use the z-score here because we have a sample size that's big enough for us to use this formula. Okay, plus 0.60 plus or minus 1.96 times 0.049. 0.60 plus or minus 0.098, double 1.96 times 0.049, roughly. Actually, it's 1.09. I think it's 6. Okay, and this would be our, I think that's got to be 4, slight little tickle in the calculations. I think that's more like it. So we're 95% sure our true population proportion for people that have this condition is between 50.4% and 69.6%. Our sample said 60%, but we're 95, that's a point estimate. The range that we're interested in is our 95% confidence interval, which says that, well, we're 95% sure it's between 50 and say 70%. Doesn't mean that we know for sure, but we're that confident. If we wanted to be more confident, we would have said 99% confidence interval and said 2.58 here. Okay, so I'm rushing through this a little bit because I know we're a little bit short. We started a little late. We're a little short on time. But I'm going to go through another example now. A random sample of 64 adults between 30 and 50 years old results in an average consumption of 4.5 alcoholic drinks per week. Right? A previous study determined with a high level of confidence that the population standard deviation is 1.6 drinks per week. Determined a 95% confidence interval for weekly alcohol consumption. Okay, so we're going to take this one step at a time. And the first step we're going to take is going to be, let's see here. Let's see if I can't get this. Okay, let's see. Okay, first thing we're going to do is we're going to ask I can't see standard. What do you think the standard error for this sample is going to be? Okay, and I gave you a few choices there. Do I have an opinion on what the standard error is going to be? Can you guys see the poll so that you can click in answers? By the way, you can't. I can't tell who's doing what, so it's an anonymous poll. So feel free to take a guess if you need to, and you won't be embarrassed by by a wrong answer or anything like that. Oh, let me go back to this. Okay, so I'm going to go ahead and close the poll, and let's see what we got. We got the most popular answer was 0%. Okay, for the standard was excuse me, the most popular answer was there were two most popular. Well, close. The most popular answer was 5, and the second most popular answer was 4. Okay, well, what's the standard error going to be equal to? The standard error. Let me see if I have it here. Is there a better way for me to do this? Okay, I'm gonna do it here from scratch. Let me get a text box here. Okay, so my standard error is going to be equal to, what is it going to be equal to for this? It's going to be equal to the standard deviation of the population, which was 1.6, divided by the square root of the sample size. Okay, sample size was 64. Okay, so standard error is going to be equal to 1.6 divided by 64. Square root of 64 is 8, divided by 8. It's going to be equal to 2. So our standard error is going to be equal to 2. Okay? You lost the question because I closed it out. Oh, you can't see the question at the same time. Okay, I'll repeat the question out loud then. Okay, next I'm going to ask you, okay, so now the standard error is equal to 2. What's the margin of error for this situation? Okay, now I'm going to have to see if I can't do something to get you. Does that help to, oh, I know what I can do. Hang on a second here. I see it behind you. I'm going to make sure you can see it then. Whoops. Okay, let me do this one more way. Just got to do a little jockeying around here so you can see it. Okay, there you go. So go ahead and take your give yourselves a chance to give it an answer. Margin of error. Remember, we just calculated the standard error was equal to 2, right? So calculate what you think the margin of error is. Okay, I'm going to give you 30 seconds to answer it, and then I'm going to close the poll. Okay, so the most common answer, 63% of you said it was 0.392. Okay, let's calculate it. Okay, margin of error is going to be equal to, it's going to be equal to the z-score for 95% confidence interval. We know the population mean, so we can use the z-score 1.96, right? Times the standard error, or 2, right? Is going to be equal to our 3.92. Okay, so those of you who said 3.92, which is the majority of you guys, were correct on that. Okay, so now, next, let's see what we got next. What's the 95% confidence interval now? Okay, and let me bring that forward so you can see that. Try and get it somewhere where you can get to that and see the question as well. Okay, 95% confidence interval. How are we going to figure that out? We know our margin of error is about 4. We know the mean that we calculated was, where is it? That was 10, was 4. Did I get the margin? Oh, it's 0.3. I'm sorry. It's point. Did I get it right? Standard error. Yeah, I think I did. 1.6. Okay, and I'm going to. Oh, I think I made a mistake there. 1.6 divided by 8. That should be, yep, that should be 2.2. Excuse me, that should be 0.2. And this should be 0.2. And this should be point. Okay. So I'm going to close out the poll. Okay, and our answer there was, its most popular answer is 4.008 to 4.89. Okay, let's see if that's correct. Okay, so our confidence interval is going to be equal to x bar, which in this case was 4.5, right? The average for the population was 4.5. Okay, plus or minus the 95% confidence, plus or minus the margin of error, which was 0.392. It's actually going to be, that's actually the standard error, 0.2 times 1.96, 3.92. So that's going to be equal to, well, I'm going to say roughly 4. It's going to be, let's see, 4.892, which is that last one, and whatever it is subtracted from that also. In other words, it's 4 to 4.892. Okay, so basically, we have a pretty good idea how this works. Let's move on, and we're going to see another couple of examples of this. Okay, next, I'm going to take a look at a situation which comes up quite frequently, where we know the mean of the sample. We know the sample standard deviation, not the population standard deviation, and it's a relatively large sample. Okay, well, in a case like this, we do exactly the same thing that we did before when we knew the population mean. We say to ourselves, okay, well, we're going, since it's such a big, a large sample, we're going to assume that the this extra error that we have because we don't know sigma, we're just going to go whatever standard deviation we have with the sample, and we're going to calculate we're going to use our z-score 1.96. We're going to calculate our standard error just like before, the standard deviation of the sample in place of the standard deviation of the population, divided by the square root of the sample size, and so on and so forth. And we'll figure out basically the same way we normally would. Sample size, if it's a large sample size, that shouldn't be a problem. If it's a small sample size, like 10, we have a problem. We don't have all that much confidence in the standard deviation being a good representation of the population standard deviation. So this starts to break down. We really can't use this effectively. We have to try something else. Let's see what happens let's see what we really should be doing when we have a small sample size. We know the mean of the sample. We know the sample standard deviation. That's the closest that we have to the population standard deviation. And we know that we have a small sample size. In this case, the sample size is 10. Okay, so we go through the exercise we normally would. See, our confidence interval, 95% confidence interval, is going to be x bar plus or minus the z-score times the standard error. Okay, but in this case, we're not going to use the z-score. We're going to substitute for the z value, that 1.96, a number which is typically larger to make up for the extra uncertainty from not knowing the standard deviation of the population and having to use the sample standard deviation. We're going to go to a table that's going to summarize that number for us. Okay, and that's called a t-table. And you have that in the Agresti. T-table is laid out a bit differently than the z-table. We don't have every area available in here. We just have the ones that are important to us. What we need for the 95% confidence interval, 99, 90% confidence interval, and so on and so forth. Okay. In terms of like which of these values we want, the column we're interested in is going to be the 95% confidence interval. This column right here. If we want 90% confidence interval, we use this column. 99% confidence interval, we be using this column. That represent a t-score or a z-score that is valid for a tail on both sides. They say right tail, but on both sides of 2.5%, representing, just like we saw before, representing a range in the middle of 95%. Okay, so now to find out what that value should be in place of z, the t value that we want to use, we are going to go down this column. Notice it has degrees of freedom. As you heard before, instead of using sample size, we're going to use degrees of freedom. Degrees of freedom is typically the sample size minus 1. A simple way to look at degrees of freedom might be, for instance, say to yourself, well, if I have a sample size of 1, I pick someone out of a population, ask them their age, and they're 32. There's no degrees of freedom there. You only have one choice, the one value that you have. If you have two people, well, now you have one additional choice to what you had before. Okay, now if you go to three people, you have two choices in addition to what you had before. And if you have 10, you have 9, and so on and so forth. So the degrees of freedom, you can look at it as the number of choices that you are given minus 1. Okay, so that one person would be no degrees of freedom. Okay, so in our case, we have a sample size of 10. So we're going to use the line for 9 degrees of freedom. And the 95% confidence interval for 9 degrees of freedom would be represented by 2.262. Notice that number is bigger than 1.96 for a 95% confidence interval. The reason why that number is bigger is because that's going to give us a wider interval. It's going to make up for the increased uncertainty that we're seeing because we're cheating a little bit and using the sample standard deviation instead of the population standard deviation, which we don't know, and because we have a small sample size. And you'll notice the smaller the sample size is, the bigger that number is. So instead of 1.96, we're going to use 2.226. Okay, now standard deviation, standard error is equal to standard deviation over the square root of n. In this case, standard error is 10, sample size is 10, square root of 10 is about 3.2 something. Standard error is going to wind up being equal to 3.16. Okay, 3.16, right, is our standard error. Our confidence interval then is going to be 100. That was our mean for our sample, plus or minus our margin of error, which was 2.226, our t-score, times 3.16, or about 92 to 108. Okay, that's going to be our 95% confidence interval. Okay, let's try another exercise here. In a random sample of 16 students, results in an average of 10.5 hours per week spent studying. This sample had a standard deviation of 4 hours per week. Determine the 95% confidence interval for the true mean hours per week of study. Okay, so the first question that I have for you is kind of an obvious one. Should you use the t table or should you use the z table for this example? Okay, I don't think you need to see the question there. Should you use the t table or the z table in this case? Okay, 47%. We have 47% of votes in. 58% of votes in. Another 7 seconds. Here we go. Any more? Any more takers? Okay. Remember, I can't tell who's giving me what answer. Okay. Uh, we got 100% out of 58% of people voted. We got 100% said the t-score, and you recognized it correctly. We're dealing with a sample standard deviation, and we're dealing with a small sample of only 16 students. So we have to use the t-score. So let's calculate these various values. First of all, let's calculate the standard error for this study, for this sample. Okay, standard error is going to be equal to, and I'll launch it. Okay, you guys tell me what would you say the standard error is? Okay, here we go. We got a little bit of a disagreement there. Okay, let's see. Okay, another 5 seconds or so. Okay. Okay, I'm going to close out the voting. Okay, got almost a 50-50 split between 3 and 1. So let's take a close look at this. The standard error is equal to the standard deviation over the square root of n. So the standard deviation was 4 divided by the square root of the sample size, right? Sample size is 16. Square root of the sample size is 4. 4 divided by 4 is 1. The standard error should be 1. Okay, you guys that said we had a lot of people said 3. Is there a reason why? Do you guys see why it might be 3? Are you guys comfortable with what I just did there? I'm gonna move on to that, but I'm a little concerned that I want to make sure that you guys recognize that 1 is the right answer rather than 3. I'm not sure how you got 3. Let's see, 16. Square root of sample size, maybe square root 16. I'm not sure. Okay, we'll figure that out. But that's how we would get it. It's 3. Okay, so now that we know that the standard error is equal to 1, right? Next, we got to calculate what t-score that we would likely to be used. Okay, I'm going to put up the t-table. I'm going to put up the t-table. And remember, our sample size is 16, and our confidence it's a confidence interval. We want 95% confidence interval. So let me pop that open. Here's our t-table, and I'll let you type this in because I don't have a poll for this one. But I'm going to tell you that, okay, this column here in the middle is what we're going to want, the 95% confidence interval. Okay, and so what do you guys think we would want to use for the t-score in this particular case? Couple of guesses? Which one of these numbers? Okay, let's see, 2.31. Okay, okay, good. 2 point. We get a lot of people saying 2 point. Right, we would want to use this number, this value for the t-score, because it's 15 degrees of freedom, right? Sample size was 16, 15 degrees of freedom, and this is the column that represents a 95% confidence interval. So when we go back to our question, okay, t is going to be equal to 2.131. Okay, so now we know that the standard deviation, let me just pop that in there, is equal to 1, and t is equal to 2.131. Okay, so now let's see if I got the next page. Okay, so now we've got this is equal to 1, this is equal to 2.131. I'm going to go ahead and type those in there. That's equal to 1. This is equal to 2.131. So the next thing we have to calculate is our margin of error. Okay, and I'm going to put up a poll for our margin of error. Okay, let's see what you guys think the margin of error might be. Okay, remember, margin of error is going to be just this part over here, t times the standard error. Right? Can you guys, I'm not sure. Did it let you change your answer? Okay, when I mentioned that, I see a few answers changing there, right? Okay, 86% of you agree that the answer is 2.131. And indeed, the answer is 2.131. I'm going to close the poll. Okay, and the answer is 2.131 because, next week I'm definitely going to have my graphics tablet. So I'll get to the Apple Store, pick up a graphics tablet so that I can actually write on the screen here and stuff like that. All right, it's going to be equal to x bar plus or minus what's going to be 2.131 times the standard error, which is 1. So that's going to be equal to 2.131. Okay, and now all we have to do is take our margin of error and add it and subtract it to our mean, our sample mean, in order to get our 95% confidence interval. And I'll give you a chance to give me the 95% confidence interval now. I got to figure out a way to get this window to fit in here a little bit better with the actual question. Oops. See, I'm not sure what you're seeing there. I'm going to have to, I think for at least one session, I'm going to have 2 computers running so I can see what you actually see here. I'm going to leave it up there. Hopefully you'll be able to see it. Okay, so I'll give you guys a second to figure that out. Another couple of sections. You're able to click that despite the fact I was dragging it all over the board. It must have been like we used to, in psychology many, many years ago, there used to be something called a pursuit rotor experiment where somebody had to take a rod and keep it on a little dot and stuff like that. Kind of similar to that. Okay, I got 83% of you saying it's between 8.369 and 12.31. Okay, let's see what we got here. Okay, so now if I'm going to calculate this myself, I would say it's equal to x bar, which was 10.5, plus or minus our standard error, our margin of error, which is 2.131. Happened to be 2.131 times 1, but that's just a happy coincidence for us. So I would say that that's going to be roughly, what is that? That's 8.369. To add that to the 12 was going to be 12.631. Okay, so that's the answer. That most of you got that answer correct, and that's how we deal with this. Okay, you got to recognize the fact about whether you should use the t-score or the z-score. You're going to determine that based on whether you know the population standard deviation or not. Number one, if you know the population standard deviation, you can stick with z. If you don't know the population standard deviation, then it's dependent on the sample size. If the sample size is very large, many times you can forget about the t-table anyway. Let's take one more close look at the t-table so that I can bring this up. Let's say our sample size, let's look at the value that we're going to use for t for a 95% confidence interval. If the sample size is 5, go to 4, it's 2.7, pretty big number. Sample size gets bigger to 10 or 11, it's 2.2. Gets bigger, let's say sample size of 20, we use 19, 2.09. If the sample size is infinite, it's 1.96, just like the z-score. And if it's 100, it's 1.98. It's almost the same as the z-score. On a practical basis, most statistics courses will tell you that if the sample size is larger than 30, use the z-score, use 1.96. Don't bother with the t-table at all. Okay, it's a little bit of a guess. It's a little bit of a cheat, right? But it saves you a little bit of trouble, and it really doesn't make that much difference. It only makes about 4% difference in the value that you're going to wind up, 4 or 5% difference in the value that you're going to wind up with once you get over, or less, once you get over 30. Okay, and you can see it's converging to that value of 1.96. Okay, which makes sense because if it was really infinite, it's almost like knowing the population standard deviation anyway. So if you got a small sample size, if you know the population standard deviation, you can use the 1.96. If you don't know the population standard deviation, you have to take a look at the sample size to decide whether or not to use the 1.96 or go to the t-table to get that value. Okay, let's see if we got something else we want to talk about.